Maybe then.
Right. Hello, I'm Michaelan Apted, and welcome to my senior TED Talk on the robotic arm. I'd like you all to meet Scarlett Tipton, a 2-year-old child who tragically lost her arm to cancer. In order to live a normal life, she has to pay $70,000 on a prosthetic arm that will need to be replaced every single time she outgrows it. In the US alone, there are 50,000 more cases like this every single year. These people oftentimes don't have the money or even the access to get the prosthetics they need. Which leads us to the question, how can robotic arms be optimally designed and manufactured to be affordable and accessible to those that need them? In order to understand how we can create an optimal robot, let's first take a step back and understand what a robot is. At its base, a robot is simply a machine, programmed with an objective it needs to complete. A robotic arm is designed to execute all the actions required of a normal human arm. A robotic system is made up of 3 components: the mechanical structure, the actuator, and the controller circuit. The mechanical structure of a robot is like the non-electrical components of it. It's like the base, the skeletal structure of the robot. The mechanical structure is not capable of moving on its own and is instead run by the actuator. The actuator is everything that's responsible for movement within the robotic arm. It's made up of a battery. Right here I have a 12-volt battery with 2 prongs that can then be connected through a wire to a motor, which is right here. The way a motor works is when it's given energy, it rotates, and then the shaft at the end can be connected to a gear or something else within the mechanical structure, causing it to rotate and move. The controller circuit is kind of the brain of the robot. It tells the actuator when and how to move. And it does this through sensor feedback. So there's a large variety of sensors: temperature, force, position. The most commonly used in bioengineering is a muscle sensor, which is capable of detecting changes in muscles being used and their intensity. So for example, if I had a prosthetic arm that was just my forearm here and my hand, I could have a muscle sensor attached to my bicep. And then when certain muscles are being used and their intensity is being tested, then the arm can move according to how my muscles are being used in my forearm. Does that make sense? And so there are also other sensors like neurosensors, which can detect brain waves and control a prosthetic exactly like a robotic arm. And now a controller circuit knows what to do based on your programming. So the way most coding works, at least in engineering, is it tests for a condition, and then if that condition is true, something happens. So take this flowchart, for example. There was a condition. In the example I listed, X muscle is being activated. If that condition is true, then we perform an action. And so the way an entire robotic system works is we have the controller circuit directing everything within the robot, and then we have the actuator moving everything along the mechanical structure. And now that we have a general idea of how a robot works, we can move on to how we can optimize it. How we can make a robot and maximize its accessibility and affordability. We can do this through 3D printing and open source distribution. 3D printing is the process of making a physical object using a 3D printer. This is done by melting down a material, usually a plastic or polymer, and then building it layer by layer. So a way to think about this is 3D objects are really just a bunch of 2D objects stacked on top of each other. Like a cube is just an infinite number, not infinite, but a lot of squares stacked on top of each other. This is the way a 3D printer prints. It starts with one layer and finishes that, then another layer on top of it. And over several hours, you eventually have a 3D object. And so I have a little video here that can kind of demonstrate it better than I can say it. So this is just essentially a time lapse of a 3D printer in action, so you can get a general idea. So the 3D printer can essentially make any 3D object that you want. Now the printer knows what to print by the CAD file that you've imported. CAD or CAD stands for Computer Aided Design. There were a multitude of different programs that allow for CAD design. This is just an example of SolidWorks, which is a program that I use a lot, and essentially it's just like an artistic design tool in which you can create solid form 3D objects however you want. And then these files can be imported to a 3D printer to print those objects physically. And anybody across the world who has this file can then print the same object on their own 3D printer. Now the material that these objects are printed out of depends on what you supply the printer with. Typically, these are polymers, plastics specifically designed for 3D printing, most notably known as thermoplastics. The plastics range broadly in terms of elasticity, durability, and cost. You could have some that glow in the dark. Like, there's just a broad range. There are even some special printers capable of printing in metal, such as steel and bronze. The thermoplastic that I found to be most effective is called Gel, which is shown here. The plastic is created from a highly elastic polymer specifically designed for prosthetics. It has the same elasticity of skin as well as the same durability as bone. The main aspect, or the main benefit of 3D printing is the significant cost reduction. Like here I've put across like a very rough assessment of how much it takes to basically produce a 3D printed robot. So like your average 3D printer is going to cost around $1,000, though I found some as cheap as like $200. And then there's enough thermoplastic material here to print basically 2 kilograms of polymer, and like motors, sensors. It's just a rough generalization. But basically I've determined that it costs around $1,500, which is significantly cheaper than the $70,000 that you can buy a normal robotic arm on the market. And it's important to know that this is worst case scenario. This is if you have to buy your own 3D printer specifically for this and solely for making your own robotic arm, which is honestly, frankly, quite silly because you can do so much with 3D printers. You can make art, you can make wallets, tools. If you're Kyle, you can make cats. So even if you don't want to buy your own 3D printer, there are options. Across the country, there are public 3D printers, far more than most people think. This picture is actually taken at the Denver Library, where they're unveiling their new public 3D printers that anybody can use free of charge. In almost every major city in the US, there are public printers just like this. Even at the fort, there are printers that you can use. I don't know if it's just for students, but eventually it'll probably be open to the public. And this access to 3D printers is only going to expand throughout the future. So the use of 3D printing offers a significant cost reduction. You know, $1,500 is a lot less than $70,000. But this means nothing if people still don't have access to this technology. That's where open sourcing comes in. When a product is open sourced, that means it's completely public. Anybody can edit, access, or distribute every single aspect of it. It's kind of like Google Docs, where anybody has edit access. Now, the problem with Google Docs is you're going to have people like me who just delete the whole thing for fun. So, it's important to note that when you're open sourcing products, people who access it aren't really editing the original files themselves, but creating copies, which they can then edit and upload on their own. I should get a show up. Sorry, I was hungry. So the open source model benefits both consumers and the project itself. Open sourcing allows people to have unparalleled access to electronic files. With a simple download, they can have the CAD file, the programming, the materials list, every single essential file they need to create their own robotic arm. The obvious downside to this is they'll have to assemble it themselves. It's kind of like a Lego booklet. And so it's important that there are instructions, video tutorials, simple enough that the average person can build their own robotic arm with one hand. So, additionally, open sourcing opens the doorway for extreme customization. Every single person's needs are different. Everybody has different arms, obviously, so it's important that this customization matches that broad diversity. You know, there are people with extremely small arms, extremely big arms, and if you're buying a robotic arm on the market, you're not going to get that exact size. So it's very important that as a consumer, you can access these files and edit them yourself. The customization can also be a lot more complex. It can match your daily life and the applications you use your arms. If you're an Olympic weightlifter like me, then you probably need a really strong robotic arm, you know, a strong material, a more powerful motor. Whereas if you're Scarlett, the little girl from before, not doing much heavy lifting. So it's important that even the simple mechanics inside the robotic arm are customizable. Additionally, the open sourcing method comes back to the project itself and helps it. Every single aspect of the robotic arm can be customized and improved upon. People across the world can pitch in and evolve the project. This is really great for me because I don't have to do anything. This project will be in a constant state of evolution as more and more people improve upon it. Programmers can update the code, make it run more smoothly, use more advanced sensory. Engineers can make the models more cost efficient, more durable. Even marketers can reach out to more people, get them involved, both consumers who need the product and people who can improve upon it. The changes don't even have to be strictly better, but just different, better suited to different applications. Like in the end, this project isn't really a robotic arm, but instead the means to create a robotic arm. And so it's very, very, very important that this project be open sourced so that it can constantly evolve and morph into something else. It doesn't even have to be a prosthetic arm. It could be something used for industrial purposes. It could be a prosthetic leg. Like, the options are limitless. And so by utilizing 3D printing and open sourcing, cheap and customizable robotic arms can be available at everyone's fingertips. This project serves to get technology to people that need it most. This is the future of engineering. Thank you very much.
All right, thank you, Michaelan. We will open it up to questions from both our audience and our panel. So, as far as open sourcing your product, do you see it being an issue amongst people with everyone having access to it? Do you see someone eventually being like profiting off of it in a bad way, where it's like, oh no, this is my design, I took it now, and using the basis of what you gave them or whoever it was that gave them, and trying to make their own thing out of it, not like giving credit or paying royalties or anything? Do you see that being an issue, like with it being so open to everybody using it? Do you see any form of problem coming out of that?
So you're asking if, like, I'm afraid of people just taking my work and profiting off of it?
Pretty much.
Okay.
More or less.
Yeah, I think it's very important that this is a big legal aspect of the project. I didn't really look into it, but I think it is important to have, like, open creative licenses on the robotic arm. Like, definitely once this is initialized, I think it's important to, like, contact lawyers, legal staff, and be able to make sure that I have a license on this work so that anybody using it, maybe selling it, also has to pay credit back to me, or perhaps I should make it that they can't sell it at all. I haven't really decided that aspect yet, but that's definitely something to be concerned for. Lloyd?
So I'm skeptical of this concept. Because you basically just told me that you can make a $1,500 arm that's equivalent to a $70,000 arm. And I'm not sure I believe you. So what are the differences in terms of like strength, durability, sensitivity between the, like, what are my trade-offs here? You haven't given me any downsides to this, which makes it feel a little shady, Michaelan.
Con man. All right. So I would say the main downfall is durability. Like, plastic is never going to be as strong as metal. I think something that is really important about 3D printed art is you have to replace them pretty frequently. I'd say every few years, because they will break, they will become wear down. Whereas with a normal robotic arm, you could use that for at least a decade, I'd say. So that's definitely one downside, but like overall the cost is just so significantly less that I'm very confident that 3D printing robotic arms will.
Do you lose other
surpass it.
performance aspects? Like, I know that the technology of prosthetics is pretty incredible these days as far as like sensitivity and like, you know, like the idea of grabbing something with a hand but like not with just enough pressure to hold it and not crush it and not drop it, right? Like do you lose some of that with these sort of self-produced arms?
Absolutely. Like, that's really where open sourcing comes into play, though. Like, I personally am not skilled enough to make a robotic arm that runs off of neurosensory. I don't have the skills to do that, but someone else does. And that's what's really great about this project, is that even if I don't have the tools or the skills to create something like this, like, neurosensory is extremely effective. I don't have the money to test it myself, but there are other people that can create a new model of this robotic arm that uses neurosensory. And
But
yes,
that would up the cost significantly,
absolutely,
right?
yes.
Okay.
So, like,
Would it? I mean, wouldn't that just be a different operating system program and not more hardware?
there is different hardware, like right now we're using a muscle sensor,
Yeah.
and then you'd need to change to a neurosensor, so you'd need like a headset that can detect these brain impulses coming from the brain. So it's both, like, one, it's more expensive, and the coding is a lot more complex. Brendan?
So you said that like a big fear of like open sourcing this would be like people deleting it. Have you like taken any like precautions to like prevent this like fear of people deleting it or like people like profiting off it or any of like the drawbacks from this?
Because you have classmates who are going to be gunning for you, so.
Yeah. I definitely want to profit off you in the future, Michaelan.
Yeah, so a big thing about this is that the original files themselves, like the project that I will be creating, is not public, but instead you can create a copy of all the files that I've made and edit them yourself. So like if you were a skilled programmer or hacker and wanted to ruin all my stuff, you'd just be ruining the copies that you have and not the original files. Does that make sense?
Yeah.
Kyle?
Okay, so $70,000 arm, right? I'm assuming that part of the cost of that is in the design and the customization to the individual, right? It's not simply materials. And so you're talking from like I hire a company to build a specialized prosthetic just for me, for my specifications,
Install
a one-time
it,
thing and
like-
install it, right, at 70 grand, versus I've got a program I essentially like download and do it yourself Lego kit, right, and not 1,500, more like 500, because you're assuming that if I'm gonna build this multiple times, I'm gonna
Yes.
buy in one printer, right? Do you see an in-between scale there, where there's perhaps a consulting company that takes the programs and alters the measurements based on, you know, the customization you were talking about, where that's not something that's a do-it-yourself, but it's also not the same level of that?
Yeah.
Is that part of the scaling
Yeah, I
process?
think that's definitely something that this project can build towards. Like, a big problem with the open sourcing is, even though people have full reign to completely customize it, they themselves don't have the skills or maybe the time to do it. And so I think it would be something that I definitely want to look for, is like prospective engineers or companies that I can hire that do all this customization for the consumers, and then they can then purchase these models for a little bit higher price.
And your program's essentially built in such a way that there's standard modifications that go
Yes.
in, like physical measurements or different.
It's basically like the way coding for robotics works, it's basically a flow chart. And so anywhere along the line of this flow, you can essentially add a new box.
Could you do it as like a drag and drop almost, where there's like the code's there in a library and you're just taking the pieces you're gonna need?
Yeah, that's
to
definitely
edit?
something you could do. There are a lot of coding programs that work like that.
Mhm.
There's something called Stencil, which actually is exactly as you've mentioned. Like, it basically takes common lines of codes and formats them into like little puzzle pieces, and you can essentially make a trail along the line of code. And
Are people gonna want to like add on to the design? Like, what's in it for them? Like, I'm talking about engineers and all the other people that you
Yeah.
talked about.
yeah, I've done a lot of research into like past open source projects, and it seems strange that because these people don't really have much of an incentive to do it, but there's actually been, know a lot off the top of my head, but there have been numerous like open source projects that have been successful just because random people who have the skills to improve upon them pitch in. And even if it turns out there's like a lack of people looking to improve, then there's always other routes we can pursue, like paying them a small wage or having different incentives built into the system.
We'll take one more question and then we've got to cut it off.
Okay?
Okay, so I'm just curious about like the differences between the 3D printed arm and the robotic, like the professional robotic.
Mhm.
Like, I know that it's cost efficient, but like what are you sacrificing with the 3D printed one in terms of like range of motion and like efficiency and like that kind of stuff? Like, are there any big sacrifices there, or are they basically the same in terms of performance?
Yeah. So basically what we have to look at is like the three components, you know, like the mechanical structure, the actuator, and the controller circuit. Everything that's electronic, like the motors and the sensors, remain exactly the same. The big thing that changes is the mechanical structure, like the material the robotic arm itself is made out of. With these, you know, professional on-the-market robotic arms, they're usually made out of really durable metal and steel that won't wear it down as easily. Whereas with 3D printing, you're stuck to plastics and polymers, which will wear down a lot more easily, but are ultimately more cost efficient, because even though they break and wear down far more quickly than the alternative, they're like magnitudes cheaper. If that makes sense, yeah.
Plus, if they broke down, you'd only be replacing the skeletal structure, right?
Yeah,
Yeah.
So
That's
much
what
of the
I said.
cost would be recovered.
absolutely.
All right. Thank you very much, Michaelan. Please step outside.